We cover topic number 12, which is momentum. We defined momentum how? There was two ways, if you remember, right? One was kind of the everyday way of thinking of momentum, the way that we understand momentum, and then there was the more scientific definition of momentum. You can give me one of them. I'm fine with that. Yeah, no?
The scientific one is has to have mass and then...
Yeah, so we'd say the scientific definition, that's the real definition, is the product of an object's mass and velocity. Where does that come from? Why do we need mass and velocity to have momentum? Well, it's because of the everyday understanding of momentum that we have, which is, yep. Yeah, it's how hard it is to stop something, right? And if something has more mass, it's harder to stop. If something has more velocity, it's harder to stop. That leads us to our real definition, which is the product of mass and velocity. Now that definition also leads us to our equation for momentum. Do you guys remember what the equation for momentum is? It's on your data sheet, so if you don't remember it, that's okay, as long as you can recognize it. What is it? If you remember it, great. If you don't, look on your data sheet and tell me what it is. Yeah?
P equals M times V.
Yeah, good. P is equal to M times V. Now there's a couple things that I want to point out again about this equation. First of all, the P is a lowercase p, right? A capital P would be, in chemistry, we'd sometimes call that pressure, but in physics, a capital P is usually power. That's not what we're talking about here. It's not at all what we're talking about. This is a lowercase p, a small p. The other thing that I want to point out is that this p has an arrow over top of it. Power doesn't. Power, just the letter p. Power is a scalar. Momentum is a vector. We know that because it has that little arrow over top of it. If it's a vector, that means that it has a direction associated with it. What's the direction of the momentum going to be? Always. Yes, the direction of the velocity, right? If the velocity is to the right, then the momentum is to the right. If the velocity is downward, then the momentum is downward. We saw that in a question yesterday, I think, example number 2, right? We wanted to find the momentum of the object as it struck the ground. The velocity was straight down. Well, the momentum was therefore straight down. The direction of the momentum is always the same as the direction of the velocity. Momentum is a vector, so is velocity a vector. Mass is a scalar, right? We probably remember that from Physics 20, but if you don't, there's always a little cheat, right? Look at your data sheet. If there's an arrow over it, it's a vector. If there's not an arrow over it, it's a scalar. What are the units? What are the units for momentum? There's two sets. One that kind of comes from this equation, and then the other one I told you about, didn't really tell you where it came from. You'll see that tomorrow, actually. Blake, what are the units for momentum? One of the two sets of units, that is.
Kilograms times meters divided by second.
Good. We say kilograms times meters per second, right? And that comes from mass, which is kilograms, times velocity, which is meters per second. The other set of units is? And this is the one that doesn't really make any sense to us right now. You just kind of have to trust me on it. Right now, what is it?
Newton times seconds.
Yeah, Newton times seconds. Not newtons per seconds, but Newton times seconds. See that I have units listed twice. It's the same thing there. Just a typo. Now, the last thing that I want to talk about here is subtopic G, which is momentum after an acceleration. The first example problem that we did yesterday said, here's the velocity, here's the mass, what's the momentum? Presumably that velocity was staying constant. But in the second example that I gave you yesterday, said, here's an object, we're dropping it from a certain height. What's the momentum as it strikes the ground? In that case, we were looking for the momentum after an acceleration had occurred. Okay, when I say that, I don't necessarily mean after something has sped up. I could also mean after something has slowed down. That's an acceleration as well, right? Be prepared for that. Okay, if you're asked to find the momentum after something has happened, that's a momentum after acceleration. Get the final velocity like we did yesterday, the final velocity, and then multiply it by the mass to get the momentum. You got that? Now, we're going to talk about this as we go through Physics 30 quite a lot, actually. In the bottom left-hand corner of your data sheet, this page right here, you're going to see a list of 10 different physics principles. It's kind of hard to see them up on the board right now. That's kind of small. But you can look at your own data sheet and see those 10 different physics principles. I want to talk about two of them here today. The first one that I want to talk about is principle number 0. Uniform motion. Says F net is equal to 0. This is a physics principle that is used whenever something is traveling at a constant velocity or if an object is stopped. In other words, if the net force is equal to 0. What's another way to say the net force is equal to 0? It's in a state of, starts with an E. It's in a state of equilibrium. So principle number 0 is really equilibrium. F net is equal to 0. It's uniform motion, constant velocity, or it's not moving. The forces are balanced. You will get at least one question on your diploma exam. I promise you this, because they tell us this is going to happen. At least one question on your diploma exam where you have to identify which physics principle or physics principles are used in calculating something and determining something. If I was to take a look at the first example question that I did yesterday, where the speed was constant, I would have used principle 0 for that, constant velocity. Does that make sense? I'll get your question in just 1 second, okay? Now, the second example question that we had, that is the momentum after an acceleration, that would be principle 1. That's accelerated motion. F net is not equal to 0. In other words, it's accelerating. It's speeding up. It's slowing down. If an object is speeding up or slowing down, it's principle 1, accelerated motion. Does that make sense? If we go back to that Physics 30 and 13 pages document for a second here. Oops, wrong one. I've got listed under topic 12 possible physics principles. Principle 0, uniform motion. I should have listed another one. What do we call that exactly? Accelerated motion. So if you're solving one of these P is equal to m times v problems, it could be principle 0 if it's a constant speed, or it could be principle 1 if it involves acceleration. So we'll look at 3 of the questions that we had for homework now, questions 6, 7, and 8 on worksheet number 1. Number 6 says, a 2.00 kilogram rock is dropped from rest from the top of a 30-meter high building. Calculate the ball's momentum, time that it strikes the ground. This is one of those momentum after acceleration problems, right? This is a physics principle number 1, accelerated motion. We want to find the momentum after it accelerates. That's the final momentum. But to do that, we need the final velocity. Any suggestions as to how to find final velocity? Yep.
VF squared is equal to VI squared plus 280.
Yeah, that's the one that I would use as well. It seems like most times you get a problem like this, that's what we end up doing. We don't have to. There's other options. If we look at our data sheet, all of these acceleration equations that we learned in Physics 20, they're all valid there, right? Like they all involve principle 1, accelerated motion. Use whichever one fits your givens. It just seems like most times this one is the one that fits the givens. Yeah, I don't know, if in doubt, try that one first. If it doesn't work for you, then try another one. Just get the final velocity somehow, and then multiply it by your mass. So let's try this one here. Let's say VF, whoops. VF is equal to, what is VI? Yeah, it's 0 meters per second because it's dropped from rest, right? If it was thrown at, let's say, 10 meters per second, then VI would be 10. How do we know which direction I threw it? What if I threw it straight down? What would VI be?
0.
Nope, 10. What if I threw it straight out this way? What would VI be? 10. What if I threw it up this straight up at 10 meters per second? What would VI be? 10. What if I threw it at an angle of 27 degrees? What would VI be? 10. Look, this is initial speed. Doesn't matter what direction it is, right? If you're using this equation, it doesn't matter whether you're throwing it straight down or straight up or at some funny angle. Okay, VI is what it is. In this case, it's 0. It's not always going to be 0. When it's not 0, though, you don't need to worry about direction when using this equation. Just sub in the magnitude of it. What's A? Yeah, we'll make it negative 9.81 because it's accelerating downward. And the displacement would be? Yeah, let's make it negative 30 again because it ends up down below where it started. We solve for VF here, and that works out to be 24.26108 meters per second. How come I didn't round that? Yeah, I don't want to round until my final answer, right? Use your unrounded number until you get to the end, to the bitter end. We're going to now multiply this mass, 2.00 kilograms, times 24.26108 meters per second. Is that good? Almost. Why did I leave that little space there in front of the 24? Because I left something out, right? That should be negative because it's downward, right? Why didn't I get negative over here?
That's velocity.
I wasn't trying to find final velocity in this equation, right? I only ever get speed from this one. But once you have the speed, if you know it's acting down, moving downward, then you can yourself put in the negative. Multiply those two together, we end up getting negative 48.5 kilograms meters per second. Now, what's the alternative to making that negative 24 and negative 48? What's the correct alternative? Yeah, we could have just said down, right?
Yeah.
We could have just used the word down. Just easier, I think, when you're doing math, to use signs and make it mathematical rather than using words. Okay? Guys comfortable with that? Okay? Okay, let's take a look at number 7. A 1 kilogram rock is thrown up into the air from ground level at a speed of 8. The ball travels to a max height and then returns to the ground. What's the rock's momentum as it strikes the ground? So let's draw this out. It might make it easier. We're starting right here at ground level at 8.0 meters per second. As we go up into the air, what happens to this rock? Slows down. 8, 7, 6, 5, 4, 3, 2, 1, 0. Stops, right? It stops, and then it turns around and comes back down. 1, 2, 3, 4, 5. Listen, if it decelerated at 9.81 as it rose up into the air, what rate does it accelerate as it comes back? 9.81. Well, if it decelerates at a certain rate over a certain distance, and it accelerates at the same rate over the same distance, isn't it going to be moving 8.0 meters per second when it reaches the ground? If you start at 8 and you slow down with a certain acceleration, and then you speed up with the same acceleration over the same distance, it's got to reach the same speed, right? Now, if you don't like that logic, do the math. Do the math. Let's say VF squared is equal to VI squared plus 2AD. VI would be 8 here, right? And A would be neg 9.81. What would the displacement be over this entire trip? 0. Right? It starts at ground level and it ends at ground level. What's 2 times 9.81 times 0? I know you guys are smart. You know how I know you guys are smart? Nobody pulled out their calculator there to multiply 2 times 9.81 times 0. Everybody knew that anything times 0 is 0. So this should be VF is the square root of 8 squared. What's the square root of 8 squared? 8. So whether you use the logic that I used initially or whether you actually calculate it, VF is going to be 8 meters per second. And now, now the question is like any other momentum after acceleration question. Whoops, that shouldn't be square though. Pardon me?
That's the longest way possible.
Did you? You know what? Okay. I'm fine with that though. Sometimes the most efficient way doesn't immediately come to our minds. Sometimes people will spend 10 minutes looking for the most efficient way. Well, that's hardly efficient to spend 10 minutes looking for an efficient way, right? If you can do the question, even if it takes you an extra step or 2 or 3 steps, who cares? Right? You got 6 hours to write this exam. You don't think that's enough time? It better be enough time. Like if you take a couple extra steps to solve this problem that nobody else took, who cares? Like you should have tons of time. Okay, if that causes you to go over on time, we got bigger issues than We got bigger issues than that. So don't worry about that at all. M is what? 1 kilogram times VF, which is, we're going to make it negative 8, is negative 8.00 kilograms meters per second. Or you could have said 8.00 down rather than negative 8. So the comment up here was, guys, that we solved for the displacement. Maybe more than one of you did this. Solve for the displacement, and then from the displacement, solve for the final velocity, and then sub that in. Is that okay? Yeah, sure it is. Like, if this question is a well-written question, then no matter how you do it, as long as you're using valid equations, not v equals d over t, because it's not constant speed, right? But one of those acceleration equations, you have to get the right answer. You have to. Unless you make some silly math mistake, but you have to. Okay, number 8. Number 8 says, a 1.5 kilogram rock is thrown up into the air from ground level, reaches a max height of 7, and then returns to the ground. What's the rock's momentum as it strikes the ground? For this one, we don't know what its initial velocity is. It's the same type of question, except that this one, we have to find the final velocity in a different way, with a different equation. It's still principle 1, right? It's still accelerated motion. We just did it in a different way. Any ideas here? Before I tell you what I did, I'd like to hear what you did if you got it. Yep.
VF squared equals VI squared plus 280.
Okay, so we said VF squared is equal to VI squared plus 280.
Solve for VF.
Solve for VF, okay.
Yeah.
But what's VI?
0.
Oh, wait a second. But it's not thrown up into the air at 0, is it?
Well, when it goes to rest from it going down.
Oh, okay, so you're only going to analyze the trip down.
Yeah.
Yes, that's exactly what I did too, actually. Yep, no, you're right. Instead of analyzing, no, that's exactly what I did. Instead of analyzing the whole trip like I did in question number 7, I just analyzed the trip down. And if I'm analyzing just the trip down, then VI will be 0 meters per second. It doesn't start at rest on the ground. The second part of a problem, as it descends from the max height, that starts at 0. It starts from rest. So analyze the trip down. Let's say VF is equal to the square root of 2 times negative 9.81 times my displacement, which is negative 7. That gives us a final speed, remember, not velocity, of 11.71921 meters per second. And then we're going to say m times v. We got 1.5 times negative 11.71921 gives me negative 17.6 kilograms meters per second. Good. How many people ended up getting 17.6? Down. Good. Excellent. Let's try another example now. This is number 3 in the booklet that I gave to you yesterday. A little bit more to this one. It says a 1,000 kilogram mass, or 1,000 kilogram car, moves at 10 meters per second. A 1,200 kilogram truck moves at 12 meters per second. We want to find the total momentum and the total kinetic energy of the system. If the car is traveling north and the truck is traveling south, and then in question D, if the car is traveling north and the truck is traveling to the west. Let's deal with one of them at a time. A first. If I want to find, let's do kinetic energy first, okay? If I want to find the kinetic energy, the total kinetic energy of the system, which is the kinetic energy of object 1 and 2 combined, the kinetic energy of the system, then I need to find the kinetic energy of object number 1 and the kinetic energy of object number 2, and then add them together. By the way, let's call this guy number 1, and let's call this guy number 2. Could you have reversed that? Could you have decided to call the car number 2 and the truck number 1? Sure. Doesn't make any difference. Ten squared is 100,000 plus times half is 50,000. 12 squared is 144. Oh, I don't know what that is. Somehow, though, remarkably, when I go to calculate the whole thing, I end up getting, lightning fast calculation in my head, 1.4 times 10 to the 5. Isn't that amazing? Let me just check my answer key. Oh, look at that. That's what I had on my answer key. It happened to be right in front of my face as I gave you that. Oh, wait a second. Did I miss something? The truck is going south, isn't it? I gotta make that negative, don't I? No, the speed, the velocity. Negative 12?
Yes.
No.
No. I'm debating.
You're just agreeable, huh? You're just agreeing with whatever I say. Why is it not negative? This is correct. What I've done is right.
Correction.
How come? No?
Because kinetic energy is not.
Yeah. Yeah. Kinetic energy is a scalar. Speed is a scalar. When I sub in scalars, I don't put in direction. I don't care whether it's 12 meters per second to the south or 12 meters per second at 37 degrees west of north. I don't care. Speed is speed. I'm not going to include direction for speed. I'm not going to include direction for kinetic energy. So that's it. Let's find the momentum now. Oh, what's the difference between momentum and velocity and kinetic energy? Besides the equation, the obvious. Yeah, momentum is a vector. I got to include direction here, right? Not for kinetic energy, but yes for momentum. We're going to say this is 1,000 times 10 plus 1,200 times 12. Is that right? No, it's got to be negative 12 because it's south.
Yes.
We multiply those together, we get negative 4.4 times 10 to the 3. Kilograms, meters per second, or we could have said Newton seconds. That would have worked as well. See the difference there, guys? The fact that we have a scalar here with no direction associated with it, and the fact that we have a vector right here, and that we need to include the direction with a vector, velocity, momentum. How about B? The car is traveling north and the truck is traveling east. How do we find the kinetic energy here? Pardon me?
West.
Yeah. West. Did I say east? Yeah, west. Sure. West and north. That's the same thing. Right? The numbers are the same. The directions are different. What difference does it make? Nothing when we're talking about kinetic energy, right? Because kinetic energy is a,
Scalar.
and speed is a, yeah, speed is a scalar. So we're going to say the kinetic energy is 1.4 times 10 to the 5. As long as the numbers don't change, then the value of the kinetic energy won't change. Will the momentum change? Yes. The momentum will be different. The direction matters here. We were going north and south. Now we're going north and west. Any ideas for this one? I don't know. Couldn't we make just west negative? Like we did south and get the same thing? How come? Scout, how come?
Don't we have to do like the drive?
Yeah, that's exactly what we got to do. This goes back to physics 20, vector analysis, right? We have object number 1 going north. We have object number 2 going west. the momentum of the system is the sum of those. But the sum of those has to be found vectorially with a triangle. I always say that this is like elementary school math. We're adding numbers together. Sometimes we have a negative in there, but we're just adding numbers together, right? Like the old-fashioned way. 3 plus 4 is equal to 7, right? Sometimes 3 plus 4 is equal to 1 if the 4 is a negative, right?
Yes.
But it's always a linear thing. Okay, it could be negative 1 if the 4 was a negative and the 3 was a positive. But when you get to junior high and high school, 3 plus 4 doesn't always equal 7. It doesn't always equal to 1 or negative 1. Sometimes 3 plus 4 is equal to 5 if we add them vectorially. And that's what we're doing here. Okay, we're saying the momentum of object number 1, let's find it. It's 1,000 kilograms times the velocity of 10 meters per second, which is 10,000 kilograms meters per second. Of number 2, we're going to say it's 1,200 kilograms times 12 meters per second, which is 14,400 meters per second. To add those together, we have to do the Pythagorean theorem. 10,000 squared plus 14,400 squared. A squared plus B squared is equal to C squared.
Yes.
That works out to be 1.8 times 10 to the 4.
Seven, eight, 1.8,
1.8 times 10 to the 4, yes. What's the direction? Yeah, you have to calculate it. This is our angle. We always measure the angle from the start. We have the opposite and adjacent sides, so we're going to say theta is the inverse tan function of opposite over adjacent. 14,400 over 10,000. You guys remember this from Physics 20? Really, that's all this is, right? Like once you find the momentum here, the 14,400 and the 10,000, this is a Physics 20 problem, right? The only Physics 30 in this is getting those two numbers. This angle works out to be 55 degrees.
Well, it's not a question. Why you do the triangle? How come your 2-1 doesn't come from first?
Okay, I'll get to that in 1 second here. Good question, but I'll get to that in a second. We're going to say this is 55 degrees. We've got to measure it from something, though. Let's make a little crosshairs at our origin there. Where are we measuring our angle from? Like we're going north and we're going west, right? Are we measuring it from the north or from the west? From the north. So it's west from north or west of north. Remember that from Physics 20?
Yeah.
55 degrees west of north. Now there's a question just a second ago. Why did I draw it like this instead of like this? Is that the question? Can anybody answer that? Yep. Yes. Vector diagrams always have to be drawn head to tail or tail to head, except for the resultant vector. The resultant vector is the sum of the vectors. So the vector diagram, the vectors that you're adding together must be drawn head to tail. And this isn't head to tail. This is drawn tail to tail. Okay, I've drawn it head to tail up here. Then my resultant vector isn't drawn head to tail, but that's okay because it's the sum of the vectors and the rules don't apply to that. Is that okay? One more example that I want to do with you today. This one says, this is example number 4, says the momentum of an object is 200. What does the momentum become if the mass is doubled and the velocity is reduced to 1/3 of its original value? How are we supposed to find a momentum when we don't know what the mass is or was, and we don't know what the velocity is or was. Yep, Calvin? You could pick numbers that work. I'm not a big fan of that, but you could do that. Yeah, Megan? Yes, essentially yes. You're skipping some steps in there, but that's what it ends up being for me. Yes. Here's the steps to get what Megan suggested that we just do. I'm going to write down an equation, a relevant equation. The equation that I would write down if I was given the mass and velocity. If I had the mass and velocity, how would I find momentum? M times v, right? So I'm going to say P is equal to M times v. I mean, that's not rocket science, right? That's an equation that's on our data sheet. That's an equation that we use to find momentum. But I'm going to put a little subscript there. PO is equal to M times V and is equal to 200. What do you think the O stands for? Original. You could call it old or original. The original momentum is 200. That's what it was before I make any changes to it, right? But the original momentum is also M times V. Now, my new momentum, I'm going to call that Pn. My new momentum is what? Let me fill you in on a little secret before I go any further. Remember when I told you yesterday the equation for momentum is M times V?
Yes.
I lied.
Why?
The equation is technically not M times V. The equation for momentum is mass times velocity. M times V is simply the symbols that we use to represent mass and velocity. We could have called velocity S, and then we would have said M times S, right? Or we could have called mass Q, and then it would be Q times V, right? That's simply the way we represent the equation, which is really mass times velocity. The equation will always be mass times velocity. My new momentum will still be mass times velocity, but my mass, I'm not going to call M anymore. Do you want to take a guess at what I'm going to call M now? Or sorry, what I'm going to call the mass?
2M.
I'm going to call it 2M, because I'm doubling what it was. If the mass was called M, now the mass is called 2M. It's still mass times velocity, but my mass is no longer M, my mass is 2M. What's my velocity? What's my velocity? It was V, now it's 1/3 V. So this new momentum is still mass times velocity, but we're just representing it in a different way. We're not using the symbols M and V, we're using the symbols 2M and 1/3 V. Now, I do want to simplify this a little bit. Let's multiply 2 times 1/3 and then pull it out front, and then just as Megan said, we end up with 2/3 M times V. Oh, but look at this. What's MV equal to? 200. Right? That was what we wrote down at the very beginning, right? That's what they told me in the question. MV is 200. So we're going to say the new momentum is 2/3 times 200, which gives me 133 kilograms meters per second. It's like magic, isn't it? We're able to find the momentum of something after we make changes to it without knowing what any of the masses were before or after, or any of the velocities were before or after, yet we still figured it out. It's not quite magic, but it's almost like magic. I call this technique variable value changing. We see this is not something that's unique to momentum. Okay, this is not something that we're going to spend a lot of time on right now. This is something that occurs throughout the course. In fact, if you look at your Physics 30 and 13 pages document, it's on that first page of miscellaneous stuff that we just do throughout the course. Does that make sense? So this is not a momentum problem, really. This is a variable value problem, variable value changing problem that we'll do more of this unit and other units moving forward as well. We're going to finish off class today, guys, by doing a couple of practice questions in preparation for a quiz tomorrow on this stuff. There's 4 questions here. Usually what will happen is I'll assign these for homework. We'll go over them the next day, and then we'll have a quiz the following day. And then we'll go over them in order. Today what I want to do is do these in class, but I'll assign these individually one at a time as opposed to do these 4 questions. I'll say, please do this question. And I'm not going to do it in order. I'd like you to first try at your desks number 2. Give you a minute to do that, then we'll take a look at that, and then I'll assign another one after we've gone over that one. How many people said C? Hey, good for you guys. The answer is C, Newton seconds. The one that we've used mostly up until now is kilograms meters per second, but we know that Newton seconds also works for us. You're going to see more clearly tomorrow why Newton seconds can be used for momentum. For now, just trust me on it. The next one that I want you to do is question number 4. Oops, let's get that erased quick. Question number 4, please, at your desks for the next couple minutes. The answer is B for this one. How do we figure that out? Well, let's get the kinetic energy. We say kinetic energy is 1/2 m1v1 squared plus 1/2 m2v2 squared. Let's call this one number 1 and this one number 2. It's 1/2 of 1200 times 20 squared plus 1/2 of 1000 times 24 squared. We end up getting 5.28 times 10 to the 5 for that. Make sure that you can get that. If you can't get that on your calculator, then make sure that I know so that I can help you get that. Now let's find the momentum. We're going to say m1v1 plus m2v2. 1200 times 20 plus 1000 times 24. That should give me 4.8 times 10 to the 4. Is that right? What's wrong? Yeah, I need a negative. How come I didn't put the negative in front of the 24 for kinetic energy?
Because it doesn't have a scalar.
Yeah, speed is a scalar, kinetic energy is a scalar, velocity and momentum are vectors. What does this add up to give me? 0. So my answer is B, as I said, 5.28 times 10 to the 5 and 0. Does that make sense? Good. Let's take a look at question number 3 now. This one might seem particularly tricky, but I'm going to give you a little hint leading into this one. Don't make this one harder than it has to be. That's your hint for this one. The answer for this one is B, 800. How come? Well, horizontally, there's no forces acting on this cannonball, right? It's moving through the air. Gravity acts downward on it, right? But nothing acts horizontally on it. If there's no forces acting horizontally on it, this cannonball horizontally is not going to speed up or slow down, right? If it remains at a constant velocity horizontally, then it remains at a constant momentum horizontally. So if the momentum is 800 horizontal at the top, it's 800 here, and 800 here, and 800 here, and 800 here. It's everywhere. It's the same everywhere, horizontally. Vertically, that's not the case, because vertically you do have a force that causes it to slow down and speed up. That's gravity, right? If the momentum vertically was this much here, well, here it's going to be this much, and here it's going to be this much, and here it's going to be 0, and then it's going to increase again as it goes down. Does that make sense? Horizontally, the momentum has got to stay the same. Vertically, the momentum changes. But since we have the horizontal momentum, and we're looking for the horizontal component of the momentum when it leaves the cannon, the answer is going to be the same, 800. Last one, which is ironically the first one, number 1. I'll give you a minute to deal with that, and then we'll take a look at it as a group. Last one. How many people said A? B? C? D? Seems to be split between A and C. Let's draw this out. We have a 47-gram golf ball that has an initial velocity of 70.0 meters per second, and the angle is 30.0 degrees. It doesn't matter whether you were in my Physics 20 class or Mr. Kader's Physics 20 class. You've done the same thing, but if you were in my class, we had a little catchphrase that we used whenever we saw something that looked like this. Whenever we saw an angle that was not 90 degrees or 0 degrees, we repeated a phrase that was 5 words. Anybody remember what that was from my class? Yeah.
I don't like funny.
I don't like funny angles. Repeat after me. No, stop. You guys, the last class did the same thing. I didn't say don't. I said I don't like funny angles. Good, you got it the second time around. You got it. I don't like funny angles. So what do we do if we don't like funny angles? Get rid of it. We don't want funny angles. We always want to get rid of 30 degrees. We never want to see those. So the way we do that is to take it off to the side over here. Redraw it. 70.0 meters per second, 30 degrees. 30 degrees is measured from the x, and then this is our y component right here. Let's make this 70 meters per second into a triangle with a 30 degree angle there. Let's find the value of x. Let's do that by saying cosine 30 degrees is equal to x over 70.0 meters per second. Anybody have the value of that? I don't have that on my answer key. Does anybody have that? Why do I not have that on my answer key? It's 60.62178, by the way. Why do I not have that on my answer key? Yep, Calvin? Yeah, because we're looking for the vertical component of it, right? If I was looking for the horizontal component of it, that's the one that I want. Now, to find the vertical component of it, I'll say sine 30 degrees is equal to opposite over hypotenuse. This one's easier. The y component is just 50, not 50, but 35 exactly. Now, what I like to do here is just kind of box that off. It's not essential to do that, but it's just kind of habit. I box it off just to kind of indicate that, look, this is just something I'm doing on the side. It's not the main part of the question. It's just kind of on the side. Now, what I can do if I want is replace this 70 meters per second with 60.62178, and then the y component is 35.0. And if I want, I can completely erase this 70 meters per second. It's gone. Look, it's dead to us. I don't like funny angles, so what do? I get rid of it. I take it off to the side. I turn it into an x and a y, and then I never want to use that 70 meters per second again. Never. So now, how do I find that vertical component of the ball's momentum? I'm going to say the y component of the momentum is m times the y component of the velocity. 0.047 kilograms, convert that to kilograms, right? Times 35.0 meters per second. When we do that, I think the answer was A, wasn't it? It is A, 1.65 kilograms meters per second. Yep. Yes, that's a good question. So Noah said instead of calculating the velocities like I have right here, could we have found the momentum m times 70 and then found the x and y components of the 70? Yes. I like to get rid of it first, but there's no real reason why we have to do that. Okay? In the end, I don't like funny angles. I got to get rid of it. It doesn't really matter whether I get rid of it with velocities or whether I get rid of it with momentum. Okay?